Hey, how's it going? Mr. Dent here. Today we're going to be doing some problems involving displacement with uniform acceleration. Our objectives today is we're going to apply kinematic equations to calculate displacement, time, or velocity when we are in a condition of constant acceleration. The term constant acceleration is synonymous with uniform acceleration. So if I use those two terms, please don't become confused. To do these type of problems, we have one formula that will work for a variety of problems involving uniform acceleration. So the formula is change in displacement, which is x. So if you haven't figured out by now, x in the physics world usually is talking about or referring to displacement. So change in displacement is equal 1/2 times the sum velocity initial and velocity final multiplied by the change in time. You may want to stop or press the pause button and write this down in your notes because this is going to be something you're going to be using quite a bit. Okay, so we're just going to go ahead and jump into applying this formula to some problems, and which is pretty much what you will do in this section. Okay, so our problem is Maggie applies the brakes of her car. The car slows uniformly from 15 meters per second to 0 meters per second, and she does this in 2.5 seconds. How many meters before a stop sign must she apply her brakes in order to stop at the sign? So I think a really good practice is to go ahead and identify your givens. And I've kind of already done this, but just to kind of read through and make sense of it. So she's already traveling, and so she's traveling at 15 meters per second. So that's going to be our velocity initial, signified by VI. And on this slide, it has it as VI, but a lot of times you'll see it as V sub I. And so that's going to be 15 meters per second. And then it's coming to a stop, so the VF, and you'll also see that as V sub F. For some reason, that didn't stay as a subscript, and it should be, is 0 meters per second. And so anytime you're coming to a stop or you're starting from rest, you need to be mindful of that and apply it to either VI or VF. Okay, and then the time is 2.5 seconds, which most of that's pretty obvious. So now for the easy part, just plugging in the numbers where they go and then just doing the math. So this slide pretty much shows you where everything goes. The velocity initial goes where VI goes, and the velocity final goes where VF goes, and then the change in time is 2.5 seconds. And then we just do our math, and your initial answer is 18.75 meters, and rounding that to correct significant figures is going to be 18.8 meters. Okay, so that was fairly straightforward because everything we were given was on this side of the equal sign, and we were finding displacement. But what if we're given displacement and we have to find one of those other variables? So this problem is going to involve something like that. So, and we'll go through the entire process of identifying givens and then putting that into the equation. Okay, so here we have a driver in a car traveling at a speed of 78 kilometers per hour, sees a dog 101 meters away on the road. How long will it take for the car to accelerate uniformly to a stop in exactly 99 meters? So notice we are using the term acceleration and we're slowing down. So in physics, that's what happens. It's just going to be a negative acceleration. Now for these types of problems, we don't need to know what that acceleration is. So don't be saying, well, we're not given acceleration, so how can we do this? If you use the formula does not have acceleration in it, so it will work. So let's go ahead and identify our given. So the car is traveling at a speed of 78 kilometers per hour. So that's going to be the velocity initial. However, we don't want to go with that because everything else is in, like this is in meters, and a lot of our units are in meters per second. So we may as well change the 78 kilometers per hour to meters per second. So just to do a quick conversion, just to review, so we got 78 kilometers per hour, and I'll go ahead and go after the kilometers conversion first. So 1 kilometer will be on the bottom, and that's going to be equal to 1,000 meters. So we're getting this in meters per second, and then we need to get our hours to seconds. So hours will go here, 1 hour per 60 minutes, and then 1 minute per 60 seconds. And that's going to come to, and I'll write it down here because I don't have much room on that side. It's going to be 21.66, and that's going to be repeating meters per second. So I'll go ahead and put this over here for our given. So 21 point meters per second. And the VF is going to be 0 because it's coming to a stop. So 0 meters per second. And then how long will it take? So that's what we're finding. We're finding the time. Put a question mark. And then we're given 2 distances here, but this first one doesn't really matter. You have to kind of read the problem and make sure you're not getting confused. Sometimes you're given information that you don't need. So this is definitely what we need, this 99 meters, because it says uniform come to a stop in 99 meters. So our displacement is going to be 99 meters. Again, this is just going to be a matter of plugging in the numbers where they go. So I think a good practice until you get kind of good at this is just go ahead and write the formula out. I know it's just a little extra time, and it helps you later in case something goes wrong. You can kind of go back and so it's going to be VI. You can go back and look and see, okay, what did I do, and see, maybe find your mistake on your own versus having the teacher figure out where your mistake is. Okay, so we're given the change in X, so I'll just put that below 99 meters. 1/2 is always going to be, and then we have a VI of 0, and we have a VF. Actually, that was the VF, and it doesn't matter because it's adding, so I'll put a little arrow so you know. And then the VI is 21.6, and I'm going to round that to 7 meters per second. And then we're going to multiply that by the time, which we don't know. That's what we're finding here. So, and I'm going to go ahead and go through this line by line just to show some of you that how you would whittle this down to finding time. Some of you I know can just quickly do that on your calculator in one big step, but some of us aren't that gifted. So I'm going to go ahead and do the middle part. So 99 meters is equal to, and so I'm going to apply this 1/2 times this sum, so we got 10.83, and that's repeating, and that's meters per second. Still multiply by change in time. And then we can move this over by division, and when we do that, we're going to get change in time equals 9.1 seconds. And I am incorrect sig figs, but I'm going by the original numbers, which was 78. It only has 2, that has 2, so we're good on sig figs. Okay, so that would be the case of where we know displacement and we know VI and VF and we just don't know time. Now what if we're trying to find one of those other variables? So here's a case of that. So here we have a car. It's entering the freeway at the speed of 10.5 meters per second, and it's going to accelerate uniformly for 3.2 kilometers, and it's going to do this in 2.5 minutes. So I'm going to go ahead and so it enters the speed with 10.5 meters per second. So that's going to be the VI. So 10.5 meters per second. And then the VF is what we're trying to find. This is how fast is the car moving after this time. And then, so the time is 2.5 minutes, but since we're in meters per second, we're going to need to get that to seconds. So 2.5 minutes times 60 seconds per minute is going to give you 150 seconds. Actually, I wrote that in the wrong spot. So scratch it out. So 150 seconds. And then the change in x, or the displacement, is 3.2 kilometers. So there's 1,000 meters in each kilometer, so that's going to be 3,200 meters. And so now we've identified our givens. Now we can just quickly just plug and chug. And so again, I'm going to go ahead and go through that process I talked about before. Write out your formula. Change in x equals 1/2 the quantity VI plus VF times the change in time. We can just plug numbers in where they go. So the change in x is 3,200 meters. One-half the quantity VI, which 10.5. Plus VF, which is what we're finding. And then the change in time is 150 seconds. And so I will, I didn't put a 2 under that. Okay, so I'm going to go ahead and move that half over. So I got 6,400 meters. Multiply both sides by 2. And then I still have 10.5 meters per second plus the VF times 150. And so I will move my 150 over by dividing both sides by 150, and I'm going to get 42.67 meters per second is what we have on that side, because we're dividing meters by second. So it's going to be equal to, I'm going to go ahead and drop my parentheses, meters per second, plus the VF. Subtract both sides by 10.5, and I'm going to get 32. I'm going to go ahead and give the rounded answer, 32 meters per second equals the velocity final. All right, that's that. Okay, so I've showed you 3 different problems that you could see using this formula that's useful in situations where we have displacement and uniform acceleration, and we don't know the acceleration. And so your assignment for this is going to be worksheet 2C, displacement with uniform acceleration. Now on your sheet, your assignment sheet that gives you all the little steps, I made a slight change. So when you're done with that, you can go ahead and go on to the next video and not do a quiz over this section. I'm going to combine 2C, 2D, and 2E into one quiz. So when you finish that worksheet, you can go on to the next video. This concludes this screencast. I hope you enjoyed watching this screencast as much as I enjoyed it. See you in class.